Good morning, everyone. Thank you so much for joining us here today, and I hope you've been enjoying the conference. I've been enjoying very much, so it's a pleasure to be here. So let's start. I'm George. Let me see if I can run this. Yeah, I'm George. A bit of my background, I have a PhD in physics, not computer science, but I've been gradually shifting towards computer science. I was a data scientist at Teradata, then I co-founded, and I'm now co-founder and consultant at Munidata. It's a small boutique consulting firm in Denmark. And I have an hobby, which is open source. So all what you're seeing today is essentially part of my hobby. So I started with Python, Django, Keras, Lime, so different things in Python. And more recently, I've been working a lot with Rust and Apache Arrow. And that's what I'm going to talk to you about today, right? So just a bit about Munidata. So we are a very small consulting, boutique consulting company. We work with large enterprises in the biotech and pharma space, and we are kind of a combination of data engineering and data infrastructure. One particularity is that because we work a lot in pharma, we also work a lot with GXP, so validated systems in pharma. But about that, so let's go. A bit of the outline, so I will try to go through a bit of what I consider to be anatomy of an analytics workload in a very simplified form for a broader audience, and then we will start narrowing down closer and closer to the details of that, and then I will broaden a bit. And we will have a small demo and some benchmarks about what we've been doing. So let's start very simple. One very easy way to think about an analytics workload is an ETL, right? And one very easy ETL is you have a blob file in Parquet, in some remote blob. You read it into pandas, you do a transformation in pandas, and then you write it, right? Very simple stuff, just the basics. Now, a more generic way to think about this is that we have some storage or transfer mechanism on which we receive this information, that we convert it into our in-memory format, like pandas, NumPy, Spark, Apache Arrow. Then we do some transformations on it, and finally, then we will offload it to some other, the same or other transfer storage mechanism, right? Very simple stuff. What I'm going to discuss you a bit here today, the first part, is that information is both stored and used, right? And this drives a lot of what analytics workload is about. And what I mean with this is that on one hand, we have these storage formats that are highly optimized for reducing space, for cross-language compatibility, for long-term storage in sometimes even encryption. On the other hand, we have the computation. So when we want to use information, we have to bring those highly compressed formats back into our CPU, close to our memory, and then operate on that format. And so you cannot get away from this. You really have two fundamentally different concepts here that you just need to know and deal with as part of your analytics workload. So probably a more sophisticated way of looking at this small diagram is to say that, well, we have some storage, right? Some Parquet, ORC, Arrow, stuff like that. Then on the in-memory side, we have Spark on NumPy. So Spark here, I'm not mentioning the query engine. I'm just mentioning the in-memory format on which Spark operates, or the row-based format. And when converting from one to the other, you have to first read bytes. So you have to read parts of the file that you want to get. And this usually is like file system, HTTPS. So you have to make a request to the blob storage, stuff like that. And then you have a second step, which is where you actually deserialize those bytes, so that those blobs, into your in-memory format. Okay? So you have these two operations in the read. And these two operations are very different from each other. And the reason why they're different from each other is you can look at them as what is the CPU doing when you're performing these. And one way to think about it is that on one type of operations, the CPU is sleeping most of the time. The second one, the CPU is running. Okay? So let's look at them. So when we are reading a blob file, so when we are picking bytes from S3 or something like that, most of the time what we are doing is we create the request, we send the request, and then we are just waiting for the network to reply, right? right? So our CPU is just waiting there for a response. And that's why usually you have like this async design and async architecture that allows you with a single thread to concurrently run multiple requests. And that's also very predominant in web development and web infrastructure. The other type of execution is what I call CPU bounded, or deserialization, decompression. And this is when the CPU is just running. So it's this task that you send it to the CPU, and it will stay 100%. It will just fulfill its operations. And this is an operation that is primarily using your CPU and your memory, usually, and probably some cache layers in the middle and stuff like that. And in these operations, you cannot really run concurrently because the CPU is just 100%. Like, you cannot do more than 100% a single node. But you can parallelize, right? So you can just use different cores on your computer and then just distribute that work across different cores, right? So this is the main idea. I will just draw here two colors to represent each of them. So we can go back to our diagram and say, well, there you go. So we have these two different operations that you just need to be aware of. And you may wonder, well, but once we read into memory, we no longer need to care about these operations because now we are CPU bounded, right? And this is true if you are in node. But if you're running Spark or if you're running in a GPU, you continue to have this problem. So looking a bit into like in a distributed way, like a very simple distribution would be, well, you pick your transformation, you distribute it across nodes, and when you distribute across nodes, we'll have to, well, pick the information, send it to the node, then wait a bit for the node to compute whatever he wants to compute or what you told him to compute, and then read from the node back when you have the result. And as I already tried to describe to you, well, we have a write operation, so we will have to serialize the data, send it to the wire, then wait, and then, well, after some time, read the bytes back, and then deserialize to your in-memory format. So even in a query engine, you have that concept present, always present, okay? So that's something to be in mind. So trying to summarize this first part, where I'm just describing the general behavior, we have the fact that we have to use information and to store information induces different in-memory formats, so different formats to store that information, to represent that information, and that induces traditionally different problems in how you convert from one format to the other and vice versa. The second one is that, well, then analytics is a mix between these CPU-bounded tasks and these IO-bounded tasks. And you just need to be present when you're thinking about one task or the other. Is this CPU or is this IO type of thing? Because in IO, usually you can run them asynchronous. In CPU, you need to parallelize them across cores, right? So that's the primary question. So it seems to me that control over this CPU and IO seems quite important, like controlling of how you code these operations and how you provide APIs to perform these operations seems quite important. And this is kind of the background for why Rust and why Apache Arrow. Okay, and that's now coming back to my second part of this talk. So Apache Arrow, so I will have to start a small introduction just for those who don't know what is Apache Arrow. So Apache Arrow is just an in-memory columnar format. So it is a bit like much more than that, but let's keep it simple. So for this talk you can think it like in this diagram that I had, I introduced now Arrow there, right? So you can think it like Spark, NumPy, Arrow is another format. And it's widely used in many contexts, and it's quite important for very different reasons, but one of them is that it is designed to hit a specific set of instructions that are from modern architectures. If you're familiar with AVX 512 would be one of them. Okay. So it is quite powerful. So that is, like, if you want initialization of why Arrow, let's step in with the one in-memory format. So then the second question is why Rust, and what is Rust here? So I think the easiest way for me to think about Rust is that it's a systems programming language that once you know it, it's very easy to avoid mistakes. It's like, in some sense, the compiler is very helpful. And it's system programming language, so it gives you a lot of control over how you control you initialize memory, how you allocate memory, when you deallocate it. So it does not have a garbage collector. It does not have a runtime, an asynchronous runtime. You have to like import it if you want to use it. So it's not in the standard library. And it's also very good for embedded systems. So easy to develop. As a developer, it's quite difficult to make mistakes. At least the compiler helps you a lot. You can still make mistakes, right? That's impossible to do it in a language. It's easy to parallelize because it has a very strong way of declaring how memory is allocated and who owns that memory, that piece of memory, and whether more than one user can mutate it or not, like no. Then it's very easy to parallelize. And I will demo it, how easy it is to change from one to the other, from a parallelized program to non-parallelized program. And it's very easy to hit modern instruction sets. So often, it is built on top of zero-cost abstraction. So often, you just write the program, and the program will compile to SIMD instructions, so like to the natural instructions of your CPU. And it even has like an ecosystem of doing this at runtime. So it's called like this instruction set detection. So it can change the implementation depending on your particular infrastructure architecture. It's also very easy to package and distribute. So that it's a bit like Go, right? So you just go to GitHub, you have the package, you can just use that package directly from GitHub in your library, and then it starts compiling with that package. You can also publish it in crates.io, which is just a package registry. So it's very standard, like a bit of coming from the NPM world where there is like a natural place for distributing packages. And well, this funny fact, right, is the most loved language in Stack Overflow survey. I think it's for 7 years now, consecutive 7 years. So people that use it, apparently they love it. So what I'm going to give you here is a small library that I've been working for the past 1.5 years that essentially merges these things together. You can think that it's just a completion. So it just fulfills the Arrow specification. It has interoperability with Parquet, Arrow, ODBC, CSV, JSON, etc. It's quite fast, and I will give you an example of this. And it is what I like to call safe and sound. And this means that we fulfill the Rust premise that we don't expose APIs, like we don't, as a public thing, you cannot result in memories out of bound reads or safety point exceptions or double freeze. So you don't have those types of problems that you originally need to read the documentation of a C++ library in order not to make those mistakes. So in Rust, there is a kind of a contract between developers of like that compiler enforces that tells you like, if you use this library and you use it without using a keyword in the language called unsafe, then you are safe. You will not reach this kind of bugs. Okay? And for like related a bit to the beginning of the talk, it has a complete separation between I/O and CPU-bounded tasks. And this is very important because it allows you to mix and match what you want to, depending on the constraints that you have in your query engine or on your application. So let's just check for a demo. Let's see if this works. So the first demo, what I'm going to show you is it's a very small demo. It's this cow here. Cow stands for clone on write. And I think I'm on the right branch. I was working, so I'm on the wrong branch, right? It still works, it's fine. I will just go through it. It's a bit more complicated than what I wanted. I simplified this example a bit, but now it's gone, so it's fine. So what I'm showing you here is a basic example of using Rust. So the first two lines is just an import statement, so a bit like other programming language like Python. Then you have a main statement, the main function, which is like C, C++. You just have a main of your application where it's the entry point. And here, we are just declaring a primitive array. So primitive array is just an array of integers, of floats, stuff like that. And in this case, I'm converting it to a dynamically object. So in C++, this would be a virtual function call, right? When you have a vtable and you can do this dynamic dispatch. So that would be the equivalent in Rust. And the important thing here is this line here. So what I'm doing here is we are picking the elements of this primitive array. It just has 2 elements, 1 and 2. Okay, it's very simple. But I'm just multiplying by 10. Okay? And then I'm checking like that, well, the result is 1020, right? It's very easy to understand, I hope. What's important here is that this is a closure, okay? So this is like in functional programming, just an anonymous function. You don't see this, but this line here, this line 18, will be compiled to SIMD. So it will be compiled to AVX, whatever, if your architecture supports. Okay? And we didn't have to declare anything about it here. It's just a Rust compiler will use LLVM, and we'll see, well, there is this instruction set that I can use in this computer, so I will just use it for doing multiplication, so that instead of doing a multiplication of item by item, I will do a multiplication of every 8 items or every 16 items. And you don't see this because you don't even need to worry about this. Like, the compiler will do it for you. You can be explicit and even write assembly here if you want, but in general, that's the premise of Rust, is that it will be fast, but you don't need to worry about it. Okay? So this is the first example. The second example I want to give you is more like a fun exercise. So what we are going to do is I have here a small, just clear here, I have here a small application written in Python, right, with Arrow, which is like an arrow library. And what I'm doing here is I'm initializing a table of 4 columns. And these 4 columns have 1 million entries each. Okay, so it's some strings and some integers. Okay? And there are some nulls in the middle, so you can see that there are some nulls on line 6 and 9. And then I'm going to time it, the writing of this parquet, of this table into parquet, which is a typical operation that you do when you want to write stuff. So let's do Python, and then this would be Arrow. Right, there you go. And then I'm just timing it, okay? So 103 milliseconds. We can do the same with Rust. So let's just cargo run. Yeah, I think I know what's happening now. I'm generating 1 million entries and not 1 billion entries, right? No, it's fine. I think it's fine. Yeah. So I'm generating not 1 million, right, but 100 million. That's why it's taking a bit more. So let's just put here a million, which is to make the example comparable. There you go. So what am I missing here? Of course, the example doesn't work as expected, right? No, I think it's fine. It should be fine, right? There you go. It was also counting the build time. So there you go. So you can see here, it's half of the time for writing a parquet file. Okay. The other aspect that I wanted to mention to you is the idea that it's very easy to parallelize a program and to remove parallelism in Rust. The important thing of all of this here in this program is this pariter here. So what we are doing is we have a chunk, which means 4 arrays. And then what we can do is we can either write columns 1 by 1 into the file, or we can parallelize the encoding, so the CPU-bounded part of the work, across these 4 arrays, and then write the whole thing into Rust, into Parquet. Okay? So what this pariter is doing is just parallelizing that work. So it's making sure that all those encoding, because CPU-bounded, so you can just distribute across your cores. And we can remove parallelism. So the way to remove parallelism in this case would be to just do this pariter instead of iter, you just do pariter. There you go. And then we expect this to take a bit more time. It is complaining that you don't need to use the library that is doing parallelism because we are not using parallelism, and it takes a bit more time. So even you can see that even the non-parallelized version is still faster than Arrow, okay? Which the baseline was 100 and something milliseconds. Good. So this was the first demo. So let's, who uses this library? So there are a couple of users. So DataBand, which is a data warehouse for analytics. It's one of the first users of Arrow 2. We have Materialize. You're probably familiar with. It's a very neat idea. So they use views and they materialize views, but then when you have an update in the underlying tables, it automatically updates the views. So it's a neat idea. Then we have Grafana SDK, so you're probably familiar with Grafana, and we have Polars. And polars is what I'm going to talk a bit here, because like the title of my talk was From Beats to DataFrames, so I need to now shift a bit towards the DataFrames. So let's go for the DataFrames. So polars is a DataFrame library, a bit like pandas, but it has the same or a similar API as PySpark, on which you can declare your DAG, and then you run it when you need it, like it's lazy in this context. So it allows you to push down do predictive push down and filter up push down and stuff like that. So it's written in Rust and has Apache Arrow as its core in-memory format. It has an API in Python, in Node.js, and in Rust, and it's relatively fast. So to give you what I mean with fast, so here is the benchmark by H2O on databases. It's a traditional benchmark of doing a group by over 50 Gs of data in a single node. And you can see here like a couple of query engines that you're probably familiar with. And you can see like on the top where polars is. This is already a year old, so take this into account. I don't know what to say more, like, there you go. So the second benchmark that I like to go through is the idea of like doing the join. You can also, instead of group bys, let's do a complex join here. And again, you have an equivalent behavior. And the next one that I'm showing you here is doing the TPCH benchmark, TCPH. Maybe I mistyped here, but you know what I mean. So it's essentially a standard benchmark for databases. And this SF10 means a scaling factor of 10. I think it means that it's about 10 Gs of data. And this, again, different DataFrame APIs in Python that you have available. And I placed in parentheses the transform, because if you remember this ETL step of read, transform, write, and we already have the data loaded in memory, and we are now just performing the group by and the sort and the where statement. Each queue here on the bottom is just one different statement. So the TPCH is composed by different SQL statements that you can bench against, and this is one of them. These are the first 7, sorry. Okay. So, and this is just the transform. Now let's look at the full thing. So, and beginning to end, which is including the read and write parquet. And there you go. And some part of this, like, okay, so 90% of this is because the persons that are working on this are very talented in optimizing queries and running, creating a data frame that is easy to use, but at the same very performant. Like this is just running in Python, right? Like you just pip install polars and you just run this thing. Like that's how it works. And then there is a small part here, which is what I meant with the arrow 2, that we can parallelize reading and writing of parquet. And not only parquet. This is against parquet, but you can think that we do that for all the other formats, as long as the format has a way of parallelizing. Like, for example, CSV is a bit more difficult. So trying to summarize a bit what I wanted to, I have a demo, right? You may not believe me, but we can also do the same thing with polars. So if we go here in Python, right, so we have, again, a data frame with 4 columns, 10 to the 6 elements. We want to bench the right part of that operation. So this is polars, right? Polars, audience, pleasure meeting. And I'm timing it the same way that I was timing by arrow. And there you go. And you can already see that polars, like the example that we are providing in the crate, polars is even doing something more because they know that they are doing some mmaps sometimes, and that's even improving the performance on the reads on the right side. This is mostly what I wanted to give you in terms of demo. So trying to summarize a bit what I was trying to tell you. So the first thing of the talk, if you ignore Arrow, ignore Rust, ignore polars, everything, just remember, if you have an analytics workload, you always have this problem. You have information that is stored and information that is used. So between the two, there is a non-trivial operation that is composed by these 2 ingredients, IO-bounded and CPU-bounded. It doesn't matter which programming language. I mean, you can store data uncompressed and then you don't get the benefits of storage, but as long as you need to start compressing data or using some form of parquet or equivalent, then you have this issue. You always have this issue, okay? That's the first one, and that's independent of all of this. The second one is that Arrow and Rust, in my opinion, are very suited for analytics workloads. And like one of the persons that I think first realized this was Andrew Groove, that is over there. And it's because we have this very powerful in-memory format, Arrow, and we have this very powerful programming language, systems programming language, that gives you a lot of control over what you want to do. And you saw there how easy it was, but at the same time, easy to develop. Like the compiler, compiled this big block of text it's text in the end. So from a parallelized version to a non-parallelized version by changing 4 characters, like 8 characters in total, right? So it gives you this very easy to use programming language, but at the same time provides you the performance that you get if you use C++ or C. Yeah. It's just that it provides you the interface. And generally, I think that it's important to mention that this is just some of the developments that have been happening in this community of Arrow and Rust, but there are much more than that. I think we had Daniel and Andrew that gave a talk 3 days ago about Data Fusion, which is a very impressive query engine and with very extensibility, also written in Rust. We have Polars, the developer of Polars, Richie, was also here virtually, and he gave a virtual talk. So if you want to know more about, like, this is just the small piece of it, but there is a very interesting API design and execution model on top of Polars that provides the benchmarks that you saw. And there are many other people working in this problem as a community, and I think that's very, very exciting. Yeah. And I think with this, I want to thank you very much for, we have some links. No, this is mostly for if you want to see it offline. But if you want to work on this problem and have some fun, either for learning Rust, for learning about Apache Arrow, for learning about query engines, then I think there are a lot of great things happening here, and it's a lot of activity happening. And I would like to finally thank all the contributors of Arrow 2, Polars, and all this community that has been working a lot and very seriously to bring these new developments into life. Finally, I would like to thank you for your attention, and have a great rest of the talk.
First of all, thanks for the talk. It was really nice. You explained it in a really nice way. You were mentioning in the beginning that you have this flexibility in terms of defining memory allocations and this kind of thing. And this reminded me when I used to be a C++ programmer and having to deal with all those pointers, memory pointers and this kind of thing. In terms of ease of use and developer experience, how do you think the three of them compare, like in terms of memory management and the amount of the complexity to do memory management, comparing Rust, C++, and C, for example?
Yeah. A good question, yeah. So I've used C++ at some point in my PhD life. I think the primary thing that Rust is trying to do is picking all the conventions that have formed, like the social conventions that have formed in the C++ community, in terms of if you have this pointer represents an immutable memory region. So you can read them without controlling the threading problem. Okay, so it's like a documentation string somewhere in the function. Like I give you this pointer, think about that when you are using this pointer. Or I'm giving you this pointer and this is a mutable reference, but be mindful, like you cannot call this twice and then try to mutate it. So all these rules that exist in some form already in the C++ and C community, Rust, in my opinion, Rust is essentially just bringing them to the compiler and say, it is very seldom or almost never you want to do certain things with memory because data races and stuff like that, and therefore the compiler will say, well, if you try to do that in a normal Rust program, I will not allow you to do that. However, if you really want to do that, then Rust still provides you an API to do that, and that's what's called the unsafe keyword, which says, as a compiler, I will not check for certain data invariants. It is your responsibility to check for them.
Have you done any benchmarks with the Julia DB?
With Julia, yes. So one of the, very good question, I think, you mean Julia, the programming language, right? Yeah. So the second two ones are Julia. The second and the third one are Julia, as far as I know. Like the third one is for sure. And they do have an impressive, also an impressive analytics workload. It's really impressive what they are able to do for such a high-level language.
Two more questions. I think the main one, well, if you think about Python and pandas and NumPy, basically you're running Python, but under the hood you're running C, and you have the bindings, right? So where do you think are the biggest improvements for polars, for example? Do you think it's mostly related to the capabilities of Rust, to the way that polars was implemented, or a mixture between the two, like for this big difference in terms of performance between polars and something like pandas, for instance? Yeah.
So you mean in terms of whether it's the format or whether it's the language, or, sorry, I was trying to...
If you think the biggest resource, the most significant reason for polars being more performant, is it due mostly to the resources of the language, Rust, or to the functionality that is implemented in the framework itself?
Okay, yeah, I see. So I think that to a large extent the language is, so first things is C++ allows the same thing that Rust allows, okay? Like we can write the same assembly code with both. Then the question is, I think it starts to become how easy it is for me to design a program that I can easily parallelize, for example. And I think that's where Rust really shines. So polars is very fast because it achieves a level of parallelism that is very difficult to match on a simple Rust, C++ implementation. So you would need to redesign a bit your implementation. That's the first one. I think the second one is that is the Arrow part. That takes a large chunk of the work. And I know that there are people in the Pandas DataFrames, in the Pandas community, that would like to gradually move to some of the parts. I don't know if you know, but like in Pandas, if you have a null value, the whole array gets converted to floats, right? And that's a challenge that Arrow naturally solves. But it's not the only one. Like there is some performance implications also. And then I think the third one is that, I mean, the community in polars have been making a lot of effort to optimize not only the traditional relational algebra queries, but also like things like as of and even things that more use in the quant space, like in the financial sector, which then feeds back into the overall.
I'm not a Rust user, so it could be something like silly question, but I was impressed by the performance things. So can I adapt this library into Databricks Spark or the Delta Lakes?
Yeah, so Rust compiles to native code. So from native code, you usually just need a foreign interface to call it, right? That's the principle of how these libraries usually play out. I think there is a library. I think Andrew mentioned that blaze.rs, right? I think that what they're doing is they're using Data Fusion, which is a query engine in Rust, to then run some of the DAGs, the Spark DAGs, into native code. So, but usually it's through a foreign interface. So you just define C ABI compatibility extension, and then you call your ABI from one to the other. So you still need to ship this binary, right, into your cluster, so that you can then call it. But there is a talk from Xiaosong at 11, I think, where he will describe a bit more about the advances of parquet in Spark, and those I recommend going. He's a very strong and very cool guy. And some of the things that you see here, you cannot see it in Spark, right? You don't benefit immediately in Spark, but the things that he's doing, you benefit immediately in Spark. So that is a talk not to miss.